When we map the oldest light in the universe, the ancient glow that fills all of space, almost everything matches what our theories predict it should look like. The temperature is nearly the same in every direction, the variations follow expected patterns, and the overall picture confirms our understanding of cosmic history remarkably well. But in the southern sky, in the direction of a constellation called Eridanus, there is a region that does not quite fit the picture we expect to see. This region is colder than it should be, and nobody has been able to fully explain why it exists or what created it. The cold spot, as astronomers have come to call it, spans roughly 5 degrees across the sky, which is about 10 times the apparent width of the full moon. In maps of the cosmic background radiation, it appears as a distinctly cooler patch, colored differently from the surrounding regions in the false color images scientists use to visualize temperature differences. The temperature difference is tiny by everyday standards, only about 70 millionths of a degree colder than the average temperature of the surrounding cosmic glow. Yet this small difference represents one of the most significant anomalies we have ever detected in the ancient light that fills our universe. You are listening to The Drowsy Astronaut, and tonight we are exploring one of the strangest mysteries in modern cosmology, a cold region that challenges our understanding. There is no rush in what follows, only the gentle unfolding of a cosmic puzzle that has occupied astronomers for over 2 decades now. If you enjoy falling asleep to real science explained calmly and warmly, consider liking this video or subscribing for future journeys through the cosmos. Feel free to share in the comments where you are listening from tonight, what corner of the world you occupy as we contemplate this quiet enigma together. The cold spot sits in a region of sky that ancient observers associated with the river of stars they called Eridanus, a constellation winding through the southern celestial hemisphere. From most of the northern hemisphere, this region dips low toward the horizon, visible only during certain seasons when it rises above the southern skyline. The constellation itself is unremarkable to casual stargazers, a meandering chain of relatively faint stars that lacks the brightness of Orion or the familiarity of the Big Dipper. Yet, within this unassuming patch of sky lies something that has puzzled cosmologists since its discovery in the early years of this century. The cosmic background radiation that contains the cold spot is not visible to human eyes, existing instead in the microwave portion of the electromagnetic spectrum. Specialized instruments aboard spacecraft far from Earth's atmosphere have mapped this radiation with extraordinary precision, measuring temperatures to millionths of a degree across the entire sky. These maps reveal a universe that is almost perfectly uniform, with the same temperature in nearly every direction to an accuracy that seems almost impossibly precise. The cold spot stands out precisely because this uniformity is so consistent everywhere else. One region, being measurably different, demands an explanation. The size of the cold spot contributes to its strangeness, making it one of the largest single features in the entire cosmic microwave background. Most temperature variations in the ancient light are smaller, appearing as tiny fluctuations that correspond to the seeds of future galaxies and the large-scale structure of the cosmos. The cold spot is different. It spans a substantial region of sky and presents a coherent, roughly circular shape that seems almost too organized. Its scale alone suggests that whatever created it must have operated across enormous distances in the early universe. The temperature maps that reveal the cold spot use colors to represent variations too small for any human sense to perceive directly, without the aid of sensitive instruments. In these maps, cooler regions often appear blue, while warmer regions appear red or yellow, with the overall background rendered in some intermediate color, representing average temperature. The cold spot appears as a distinctly blue patch, standing out against the slightly warmer surroundings, with an unmistakable presence in the data. Scientists have examined this feature using multiple independent instruments, confirming that it represents a real physical phenomenon rather than an artifact of measurement. The location of the cold spot in the southern sky means it was not immediately visible to the earliest cosmic background experiments, which were often conducted from the northern hemisphere. As satellite missions began mapping the entire sky from space, the full extent of the cosmic background became visible, including regions previously obscured or difficult to observe from the ground. The southern sky revealed its secrets alongside the northern, and among those secrets was this unexpectedly cold region that would generate decades of scientific debate. The cold spot was waiting there all along, present in the ancient light, ready to be discovered when our instruments became sensitive enough. The cosmic microwave background itself represents light from an epoch when the universe was only about 380,000 years old, impossibly ancient by human standards. This light has been traveling through space ever since that early time, its journey spanning nearly the entire history of the cosmos, from shortly after the beginning to now. The temperature of this radiation has cooled dramatically over billions of years as the universe expanded, dropping from thousands of degrees to its current temperature of about 2.7 degrees above absolute zero. The cold spot represents a region where this cooling proceeded slightly differently, leaving behind a patch that ended up just a bit cooler. The difference of 70 millionths of a degree might seem insignificant when stated as a number, but its significance becomes clearer when we consider the context. The cosmic background radiation is one of the most uniform phenomena ever measured, with the same temperature in all directions to extraordinary precision across billions of light-years of space. Finding a region that deviates from this uniformity by even a tiny amount raises immediate questions about what physical process could create such a deviation. The uniformity is expected, predicted by our theories. The deviation is not, and deviations demand explanations. The shape of the cold spot appears roughly circular in the temperature maps, though not perfectly so, with some irregular features around its edges and some structure within its interior. This approximate circularity has itself become a subject of interest, as certain theories predict that particular processes would create circular features, while others would produce different shapes. The fact that the cold spot is approximately round, rather than elongated or irregular, provides a clue, though not a definitive answer, about what might have created it. Every feature of this anomaly carries potential information about its origin. The statistical significance of the cold spot, the degree to which it deviates from expectations, has been debated extensively since its discovery was first announced. Some analyses suggest the probability of such a feature occurring by random chance is roughly 1 or 2%, unusual but not impossibly rare. Other analyses, using different statistical methods or different definitions of what counts as anomalous, arrive at different numbers that can be higher or lower. The debate over precisely how unusual the cold spot truly is continues, with cosmologists disagreeing about the proper way to interpret the statistics. The cold spot exists within the broader context of cosmic microwave background studies, one of the most successful fields of modern cosmology over the past several decades. Measurements of this ancient light have confirmed key predictions of the standard cosmological model, determined the age and composition of the universe with remarkable precision, and revealed the seeds of cosmic structure that would eventually become galaxies and clusters. Against this backdrop of success, the cold spot stands as an outlier, a feature that does not quite fit the otherwise elegant picture. Its presence reminds us that even our best theories may not capture everything. The journey to understand the cold spot has involved some of the most sophisticated scientific instruments ever built. Spacecraft designed specifically to map the ancient light with the highest possible precision. These missions have operated far from Earth, avoiding the interference of our planet's atmosphere, patiently collecting data over years of observation. The maps they have produced represent triumphs of engineering and careful analysis, revealing the cosmic background in exquisite detail across the entire sky. The cold spot appears consistently in data from different missions, ruling out the possibility that it might be an instrumental artifact or a processing error. The region of sky containing the cold spot holds no special significance in terms of nearby objects visible from Earth. It is not aligned with any particular galaxy or cluster or bright star in our cosmic neighborhood. The constellation Eridanus is simply where the cold spot happens to appear from our vantage point, a directional coincidence that provides a convenient name but no physical explanation. Whatever created the cold spot did so in the distant reaches of the observable universe, billions of light years away, in the epoch when the cosmic background radiation was first released. The causes lie deep in cosmic history. The mystery of the cold spot has generated multiple competing hypotheses, each attempting to explain how such a feature could exist in an otherwise remarkably uniform cosmic background. Some of these explanations involve known physics and relatively ordinary astronomical objects, while others venture into more speculative territory involving physics we have not yet confirmed. The range of proposed explanations reflects both the difficulty of the problem and the creativity of the scientists working to solve it. No single explanation has achieved consensus, leaving the cold spot as an ongoing puzzle. The emotional response to the cold spot among scientists has varied, from those who see it as a likely statistical fluctuation that will eventually be understood, to those who believe it might point toward genuinely new physics. Some view the anomaly with cautious skepticism, noting that unexpected features sometimes appear when we look at large amounts of data and do not always indicate deep truths about nature. Others approach it with excitement, recognizing that anomalies have historically sometimes led to important discoveries that reshaped our understanding of the cosmos. Both responses are valid approaches to scientific uncertainty. The cold spot continues to appear in every new map of the cosmic microwave background, unchanged by our analysis, patient in its presence, waiting for someone to determine its origin. It has been there since the light that carries it first began traveling through the expanding universe nearly 14 billion years ago. It will remain there regardless of whether we ever fully understand what created it, a feature of the ancient light that simply exists, whether explained or not. The universe does not require our understanding to be what it is. To understand why the cold spot is so puzzling, we need to understand more about the light it exists within. The cosmic microwave background, the oldest light in the universe, and the remarkable story of how it came to fill all of space around us. The cosmic microwave background is the oldest light we can see. Released when the universe was just 380,000 years old, far younger than the nearly 14 billion years that have passed since then. This ancient glow fills all of space, coming from every direction equally, a remnant of a time when the entire cosmos was hot and dense and filled with energy. The light has been traveling ever since that early epoch, crossing the expanding universe for billions of years before reaching our instruments today. Understanding this background helps us understand why a cold region within it is so strange. The story of this light begins in the earliest moments of the universe, when everything was compressed into an almost unimaginably hot and dense state that we call the early cosmos. In those first moments, matter and energy existed together in a state very different from the universe we see today, a plasma where light could not travel freely. Photons, the particles of light, constantly scattered off other particles, bouncing around without ever making it very far before colliding with something else. The universe was opaque, filled with light but not letting that light travel through empty space, as it does now. The universe expanded continuously from its earliest moments, and as it expanded, it cooled, the energy spreading out over larger and larger volumes of space. For hundreds of thousands of years, this expansion and cooling continued while the cosmic plasma gradually grew less hot and less dense. The temperature dropped from billions of degrees to millions to hundreds of thousands, the universe slowly transitioning toward a state where light could finally travel freely. The moment of that transition would create the cosmic microwave background we observe today. When the temperature dropped below about 3,000 degrees Celsius, something fundamental changed in the nature of the matter filling the universe at that time. At higher temperatures, atoms could not hold together. Electrons flew freely rather than orbiting atomic nuclei, creating the plasma state where light constantly scattered. Below 3,000 degrees, electrons could finally settle into orbits around protons, forming stable atoms of hydrogen for the first time in cosmic history. This process, sometimes called recombination, transformed the universe from opaque plasma to transparent gas in a remarkably short period. The light that had been bouncing around in the hot plasma was suddenly free to travel, streaming outward in all directions without constant scattering. This moment of release is sometimes called the surface of last scattering, the cosmic moment when photons began their long journeys through space without interruption. The light that escaped in every direction at that moment has been traveling ever since, spreading through the expanding universe, its wavelength stretching along with the expansion of space itself. That light, stretched and cooled, is what we now detect as the cosmic microwave background radiation. The original temperature of this released light was about 3,000 degrees, giving it a warm orange glow, similar to the light from a heated metal surface. But the universe has expanded enormously since that time, and the expansion of space stretches light along with it, increasing wavelengths and decreasing energy. Light that was once visible to human eyes has been stretched into microwave radiation. Invisible to us, but detectable by specialized instruments designed for that portion of the spectrum. The current temperature of this radiation is about 2.725 degrees above absolute zero, the coldest possible temperature. The uniformity of the cosmic microwave background represents one of the most remarkable features of the observable universe, a near-perfect sameness across all of space. In every direction we look, the temperature is the same to better than 1 part in 10,000. A level of uniformity that seems almost impossible for such a vast and ancient system. This uniformity tells us something important about the early universe. It was extremely smooth, with matter and energy distributed almost evenly throughout the entire volume that would eventually become our observable cosmos. The smoothness is a puzzle itself, one that theories like cosmic inflation attempt to explain. Small variations do exist within this overall uniformity, tiny fluctuations in temperature that appear as subtle patterns in the cosmic microwave background maps. These fluctuations, typically about 1 part in 100,000 of the average temperature, represent slight differences in density that existed in the early universe. Regions slightly denser than average would eventually attract more matter through gravity, growing into the galaxies and clusters and large-scale structures we see in the universe today. The fluctuations are seeds planted in the early cosmos that grew into everything we observe around us now. The pattern of these fluctuations follows statistical rules that our theories predict with impressive accuracy, the same in all directions, with particular sizes of variation being more common than others. Cosmologists study these patterns in detail, extracting information about the age, composition, and history of the universe from the subtle variations in an ancient glow. The success of this field has been remarkable, providing some of the most precise measurements in all of science, confirming predictions made decades before the measurements became possible. The cosmic microwave background has become a cornerstone of modern cosmology. The cold spot stands out against this context because it does not fit neatly into the expected pattern of fluctuations that our successful theories predict. It is larger than typical fluctuations, colder than expected for a region of its size, and appears as a coherent feature rather than a random variation in an otherwise smooth background. While fluctuations should exist and do exist throughout the cosmic background, the cold spot seems to exceed what we would normally expect to find anywhere in the observable sky. Its presence challenges the otherwise excellent agreement between theory and observation. The cosmic microwave background was predicted, theoretically, before it was ever detected. A remarkable example of theoretical physics anticipating observational discovery. In the 1940s and 50s, physicists working on cosmological models realized that a hot, early universe would leave behind a remnant glow of radiation filling all of space. The temperature of this remnant was predicted based on the physics of the early cosmos and the expansion that followed, giving observers a target to search for. When the radiation was accidentally discovered in 1965, it matched the predictions closely, confirming the basic picture of cosmic history. The detection of the cosmic microwave background in 1965 came from 2 radio astronomers at Bell Telephone Laboratories who were puzzled by a persistent noise in their antenna that they could not eliminate. Arno Penzias and Robert Wilson eventually realized, with help from theoretical cosmologists, that they had detected the ancient light that theory had predicted should exist. The discovery earned them the Nobel Prize and transformed cosmology from a largely theoretical field into one that could be tested with precision observations. The cosmic microwave background became accessible to study. Subsequent decades brought increasingly sophisticated measurements of the cosmic microwave background. Each generation of instruments revealing more detail and confirming theoretical predictions with greater precision. The Cosmic Background Explorer satellite, launched in 1989, made the first precise measurements from space, above the interference of Earth's atmosphere. The Wilkinson Microwave Anisotropy Probe followed in 2001, mapping the background with much higher resolution and revealing the detailed patterns of fluctuations. The Planck satellite, launched in 2009, achieved even greater precision, creating the most detailed maps we have ever made. These maps reveal the cosmic background in extraordinary detail, showing temperature variations across the entire sky, with precision measured in millionths of a degree. The patterns confirm theoretical predictions about the nature of the early universe, the composition of matter and energy, and the processes that shaped cosmic evolution. Agreement between prediction and observation is remarkably good, with most features of the maps matching what our theories expect to find there. The cold spot is notable precisely because it represents one of the few features that does not fit this otherwise excellent agreement. The light of the cosmic microwave background has traveled for nearly 14 billion years to reach us, crossing a universe that has expanded enormously during that time. The photons we detect today left the surface of last scattering when the universe was tiny compared to its current extent, then traveled through billions of years of cosmic expansion. Along the way, the light has been affected by the matter it has passed through or near, picking up subtle effects from the structures that formed after the background was released. These effects can slightly alter the temperature or polarization of the light, adding additional information beyond what was present at the moment of release. The journey of cosmic background light through the universe means that features in the background can sometimes be affected by structures that formed long after the light was released. If light passes through a region of space that is expanding differently than average, the light can gain or lose energy, appearing slightly warmer or cooler than it otherwise would. This effect, related to how space and matter interact, provides one possible explanation for the cold spot that we will explore later. The light we observe carries information not just from its origin, but from its entire journey across cosmic time. The uniformity and the patterns of the cosmic microwave background together tell a story of cosmic history, from the hot, dense beginning through expansion and cooling to the formation of structures we see today. The cold spot adds a complication to this story, a feature that does not quite fit the otherwise clean narrative of cosmic evolution that our best theories provide. Its presence raises questions about whether our understanding is complete, whether something happened in cosmic history that we have not fully accounted for in our models. The ancient light holds its mysteries quietly. The discovery of the cold spot came through careful analysis of the detailed maps created by the instruments that have surveyed the cosmic background from space over the past 2 decades. The Wilkinson Microwave Anisotropy Probe, known by its initials as WMAP, launched in June of 2001 on a mission to create the most detailed map of the cosmic microwave background ever produced. The spacecraft traveled to a location about 1 million miles from Earth, far from our planet's interference, where it could observe the ancient light with extraordinary precision. Over the following years, WMAP scanned the entire sky repeatedly, building up a detailed picture of the temperature variations in the cosmic background across all directions. The data it collected would reveal features both expected and unexpected. In 2004, a team of astronomers, led by Patricio Villalva at the University of Cantabria in Spain, published the first analysis, identifying an unusually large, unusually cold region in the WMAP data. The team had been applying statistical techniques to search for structures in the cosmic background that departed from expected patterns, looking for anything that stood out. What they found in the direction of the constellation Eridanus was a region significantly colder than their models predicted any region should be. Given the overall statistics of the cosmic background, the cold spot had been discovered. The initial discovery generated immediate interest and equally immediate skepticism, as is appropriate for any surprising scientific claim that challenges established understanding. Other researchers began examining the WMAP data independently, applying their own statistical methods and looking for alternative explanations for what Villalva's team had found. Some confirmed the anomaly while questioning its significance, noting that when you search large data sets for unusual features, you will sometimes find them by chance alone. The debate about how to interpret the cold spot began immediately upon its announcement. The statistical analysis behind the discovery involved techniques designed to identify features that departed from the random patterns expected in the cosmic background. The cosmic microwave background should contain random fluctuations following specific statistical rules, with larger features being less common than smaller ones in predictable ways. The cold spot appeared to violate these expectations, being both larger and more extreme than the statistics would suggest should occur anywhere in the observable sky. Quantifying exactly how unlikely it was became itself a subject of scientific debate. Different statistical methods gave different answers about the probability of the cold spot occurring by random chance, with estimates ranging from roughly 1% to several percent, depending on the approach. A 1% probability sounds low, but it means that if we could observe 100 different universes, we might expect to find such a feature in one of them. Whether this makes the cold spot genuinely surprising or merely a statistical outlier depends on how we frame the question and what we consider acceptable levels of improbability. The interpretation remains contested. The Planck satellite, launched in May of 2009 by the European Space Agency, would provide the definitive test of whether the cold spot was real or an artifact of the WMAP instruments. Planck carried more sensitive instruments than WMAP and would observe the cosmic background at multiple wavelengths, allowing cross-checks that could identify instrumental effects. If the cold spot appeared in the Planck data as it had in the WMAP data, using completely different instruments and analysis methods, its reality would be confirmed beyond reasonable doubt. The Planck results, released over several years beginning in 2013, confirmed the existence of the cold spot in the position and with the properties that WMAP had found. The independent confirmation was significant. The same feature appeared in data from different instruments, built by different teams using different technologies, orbiting in different locations, analyzed by different methods. The cold spot was not an artifact. Whatever was causing the anomalous cold region was real, a genuine feature of the cosmic microwave background that demanded explanation. The confirmation by Planck shifted the scientific discussion from whether the cold spot existed to what had caused it to exist in the first place. Multiple hypotheses had already been proposed in the years between the WMAP discovery and the Planck confirmation, and the new data allowed tests of some of these ideas. Some hypotheses were weakened or ruled out by the Planck observations, while others remained viable though unproven. The mystery had been established, but the solution remained elusive. The data from both missions allowed detailed characterization of the cold spot's properties beyond just its existence and approximate location in the sky. Astronomers could measure its precise shape, the temperature profile from center to edge, and how it related to surrounding regions in the cosmic background. These details provided constraints on what kinds of physical processes could have created the feature, ruling out some possibilities while leaving others open. Every measurement added information to the puzzle. The shape of the cold spot appeared roughly circular, though not perfectly so, with the coldest region near the center and temperatures gradually approaching normal values toward the edges. This approximate circularity attracted attention because certain theoretical mechanisms would produce circular features, while others would produce different shapes. The geometry of the anomaly became itself a clue, though not a definitive one, about what might have created it in the distant past of the early universe. The technology behind the satellite missions that discovered and confirmed the cold spot represents decades of advancement in instrument design and sensitivity. The detectors used to measure cosmic background radiation must be cooled to extremely low temperatures themselves, just a fraction of a degree above absolute zero, to detect the faint signals from the ancient light. The engineering required to build and operate such instruments in space, far from Earth and exposed to the harsh environment beyond our atmosphere, represents a triumph of human technical capability. The teams that analyzed the satellite data spent years developing methods to separate the cosmic signal from various sources of contamination and interference. Our own galaxy emits radiation at similar wavelengths, as do other astronomical sources, and these foreground signals must be carefully modeled and subtracted to reveal the ancient light behind them. The cold spot persisted through all of these analysis steps, appearing consistently regardless of how the data was processed, adding to the confidence that it represented a genuine cosmic feature rather than a processing artifact. The scientific community's response to the cold spot evolved over time, from initial skepticism through cautious acceptance of its reality to ongoing debate about its interpretation and significance. Papers were published proposing various explanations. Other papers were published critiquing those explanations, and the conversation continued through conferences and journals and informal discussions. This is how science works. Claims are made, tested, debated, refined, and sometimes replaced with better ideas as understanding develops. The discovery process for the cold spot illustrates how modern science depends on large collaborations, sophisticated instruments, and careful statistical analysis. No single person discovered the cold spot. It emerged from the work of hundreds of scientists and engineers who built the satellites, collected the data, developed the analysis methods, and published the results. The collaborative nature of the discovery reflects the complexity of the questions being asked and the resources required to answer them. The data that revealed the cold spot remains available for analysis, and researchers continue to examine it using new techniques and asking new questions about what it might mean. Each new analysis adds to our understanding, even when it does not resolve the central mystery of what caused this unexpectedly cold region. The cold spot has become a standard topic in cosmological discussions, a known anomaly that any comprehensive theory of the universe should eventually explain. The existence of the cold spot, confirmed beyond reasonable doubt by independent observations from multiple sophisticated instruments, raises the fundamental question of why it should exist when our best theories suggest it should not be there at all. The standard model of cosmology, which describes how the universe evolved from its earliest moments to the present day, makes specific predictions about what the cosmic microwave background should look like when mapped in detail. This model has been extraordinarily successful, matching observations with impressive precision across a wide range of measurements, and confirming our basic understanding of cosmic history. The predictions include not just the overall temperature of the background radiation, but also the statistical properties of the variations that should appear across the sky. The cold spot challenges these predictions. The variations in the cosmic microwave background should follow statistical patterns that cosmologists call Gaussian random fluctuations, a technical term that describes a particular type of randomness with specific mathematical properties. In a Gaussian random field, most variations are small and close to average. Larger variations are less common, and very large variations are quite rare. The distribution follows the familiar bell curve, with most values clustering near the center and extreme values appearing in the tails with predictable frequency. The cold spot appears to sit too far in the tail. Statistical analysis of the cold spot suggests that finding such a large, cold region by random chance is relatively unlikely, with most estimates putting the probability somewhere between 1 and 3%. A 1% probability means that if the universe followed our statistical models perfectly, we would expect to find such a feature in only about 1 out of every 100 observable skies. This does not make the cold spot impossible. Unlikely events do occur, but it does make it unusual enough to warrant investigation into whether something beyond ordinary randomness might be responsible. The concept of statistical significance becomes important when evaluating how unusual the cold spot truly is compared to our expectations. Scientists often express significance in terms of sigma, a measure of how many standard deviations an observation lies from the expected value. The cold spot has been estimated at roughly 2 to 3 sigma significance, meaning it deviates from expectations by 2 to 3 standard deviations. This is notable and worth investigating, but it is not the 5 sigma threshold typically required to claim a definitive discovery in physics. The look elsewhere effect complicates the statistical interpretation, reminding us that when we search large datasets for anomalies, we increase our chances of finding something that appears unusual by chance alone. The cosmic microwave background covers the entire sky, and astronomers have examined it using many different statistical tests, looking for various types of features. If we perform enough tests, something will eventually exceed our threshold for interest, just by random luck, even if nothing genuinely unusual exists. The cold spot might be such a statistical accident. Defenders of the cold spot's significance argue that the look elsewhere effect does not fully explain away the anomaly, because the cold spot was not discovered through a fishing expedition, but emerged from straightforward analysis. The feature is large, coherent, and distinctive in ways that make it stand out, regardless of how many other tests were performed on the data. The debate over how to properly account for multiple comparisons continues among statisticians and cosmologists who approach the problem from different perspectives and reach different conclusions. The spatial size of the cold spot contributes to its statistical improbability, as larger features are generally expected to be less extreme than smaller ones in a Gaussian random field. Small variations can be quite extreme while still being statistically acceptable, but large variations covering significant portions of the sky should be more moderate, according to standard expectations. The cold spot violates this expectation, being both large and extreme, a combination that our models suggest should be rare. The shape of the probability distributions that describe expected cosmic background variations has been derived from theoretical models of the early universe and confirmed through observation of the rest of the sky. These distributions describe what should be normal, and the cold spot lies outside the normal range. The question becomes whether lying outside the normal range by this amount should concern us, or whether we should accept it as the kind of outlier that inevitably appears somewhere in any sufficiently large data set. Different researchers have reached different conclusions about how seriously to take the statistical anomaly, reflecting genuine scientific uncertainty about the proper interpretation of the data. Some argue that the cold spot is unusual enough to suggest new physics or unknown processes in the early universe, while others maintain that it falls within the range of expected statistical fluctuations, once all factors are properly considered. Both positions are defended by competent scientists with reasonable arguments. The implications of the cold spot being genuinely anomalous would be significant for our understanding of the early universe, and possibly for fundamental physics. If something beyond ordinary statistical fluctuation created this feature, we would need to identify that something and understand how it operated. The potential significance motivates continued research, even while skeptics caution against overinterpreting what might ultimately prove to be a statistical accident. The theoretical predictions that the cold spot appears to violate come from some of the most successful theories in the history of physics, developed over decades and confirmed by numerous independent observations. The standard cosmological model explains the expansion of the universe, the formation of large-scale structure, the abundance of light elements, and many other phenomena with remarkable success. The cold spot represents a small discrepancy in an otherwise excellent agreement between theory and observation. The history of science includes many examples where small discrepancies eventually led to important discoveries. Anomalies that seemed minor but pointed toward genuinely new physics that transformed our understanding. The precession of Mercury's orbit, unexplained by Newtonian gravity, eventually became evidence for Einstein's general relativity. The ultraviolet catastrophe in blackbody radiation led to the development of quantum mechanics. The cold spot might be such a signpost, or it might be nothing more than statistical noise. The current consensus, if there is one, holds the cold spot as a genuine but not definitive anomaly that warrants continued investigation without yet compelling revision of our standard cosmological model. Most cosmologists would say we should take it seriously, but not panic, gather more data, and develop better analyses, while keeping an open mind about what the ultimate explanation might prove to be. This cautious approach reflects the uncertainty that remains about what the cold spot means. The scientific community continues to live with this uncertainty, neither dismissing the cold spot as unimportant nor accepting it as definitive evidence for new physics. Papers continue to be published, analyses continue to be refined, and the debate continues without resolution. The patience required to work with incomplete answers is a necessary part of scientific practice. If the cold spot is not simply a statistical fluctuation, then something must have caused it. Some physical process that created a large, cold region in the cosmic microwave background that persists to this day. One of the first physical explanations proposed for the cold spot involves an enormous empty region of space that astronomers discovered lying roughly in the same direction as the cosmic anomaly itself. This void, sometimes called the Eridanus supervoid, represents one of the largest known structures in the observable universe, spanning approximately 1.8 billion light-years across. If light from the cosmic microwave background passes through such a void on its way to Earth, the passage can affect the light's energy in measurable ways. The supervoid seemed like a natural candidate to explain the cold spot. Voids are regions of space where the density of matter, galaxies, gas, and dark matter is significantly lower than the cosmic average. The universe is not uniformly filled with matter, but instead contains a cosmic web of dense filaments and clusters, separated by vast bubbles of relative emptiness. These voids form naturally as gravity pulls matter toward denser regions, leaving the spaces between increasingly empty over cosmic time. Some voids grow to enormous sizes, becoming the largest coherent structures in the observable universe. The Eridanus supervoid was identified through surveys of galaxies in the direction of the cold spot, revealing a region where galaxies are unusually scarce compared to surrounding areas. The void lies at a distance of roughly 6 to 10 billion light-years from Earth, placing it along the line of sight between us and the cosmic microwave background. Its enormous size and its alignment with the cold spot suggested that the two features might be connected, the void somehow responsible for the temperature anomaly. The physical mechanism that could connect a void to a cold spot in the cosmic background is called the integrated Sachs-Wolf effect, named after the physicists who first described it theoretically. This effect arises from the interaction between light and the gravitational fields it passes through, combined with the expansion of the universe that is accelerated by dark energy. When light enters a gravitational well, it gains energy as it falls in, but if the well is stretching due to cosmic expansion, it loses slightly more energy climbing out than it gained falling in. The integrated Sachs-Wolf effect is subtle, typically producing temperature variations of only a few millionths of a degree. But it provides a way for relatively recent structures to affect the ancient cosmic background radiation. Voids, being regions of low density, create gravitational effects opposite to those of dense clusters. Light passing through a void can lose energy overall, appearing slightly cooler than it would have otherwise. A sufficiently large void could, in principle, create a cold spot in the cosmic microwave background through this mechanism. The problem with attributing the cold spot entirely to the Eridanus supervoid is that calculations suggest the void is not quite large enough or empty enough to explain the full temperature difference observed. Most estimates suggest the supervoid could contribute perhaps 20 to 40 millionths of a degree of cooling. But the cold spot shows a deficit of about 70 millionths of a degree. The numbers do not quite add up, leaving a substantial portion of the anomaly unexplained, even if the void contributes to it. Some studies have questioned whether the Eridanus supervoid even exists at the size and depth initially claimed, noting that galaxy surveys in this region are difficult due to the relatively low number of galaxies available for analysis. The void might be smaller than first reported, or it might be less empty, or its distance might differ from initial estimates. If the void is less significant than originally thought, its contribution to the cold spot would be even smaller than the already insufficient calculations suggest. Other studies have confirmed the presence of an underdensity in the direction of the cold spot, supporting the basic reality of the supervoid, even while debating its precise properties. The void is real in the sense that something unusual exists in this direction, a region of lower than average galaxy density, but its exact characteristics remain subject to measurement uncertainty. The connection to the cold spot remains plausible but unproven. The supervoid hypothesis attracted attention partly because it offered a relatively conventional explanation for the cold spot, invoking known physics rather than requiring exotic new theories. If a large void could explain the anomaly, the cold spot would be interesting but not mysterious in any deep sense. It would simply be a consequence of the particular distribution of matter in our observable universe. This conventional explanation appealed to those who prefer not to invoke new physics when existing physics might suffice. The idea that the supervoid contributes to, but does not fully explain the cold spot, has become a common position in discussions of this mystery. Perhaps the void creates part of the temperature deficit, while some other effect creates the rest, the two combining to produce the observed anomaly. This combined explanation would require identifying what additional factor is involved, but it would preserve a role for the supervoid while acknowledging its limitations. Searches for other voids that might contribute to the cold spot have not revealed additional candidates of similar size, leaving the Eridanus supervoid as the primary known structure in this direction. The alignment between the void and the cold spot might be coincidental, or it might indicate a genuine connection that is simply too weak to explain everything. Distinguishing between these possibilities requires better measurements of both the void's properties and the cold spot's characteristics. The debate over the supervoid continues, with different researchers reaching different conclusions, depending on which data they use and how they analyze it. Some remain convinced that the void explains most or all of the cold spot, while others argue that the void is essentially irrelevant and the cold spot requires a different explanation entirely. The scientific literature contains papers supporting both positions. The supervoid hypothesis represents the most straightforward physical explanation for the cold spot, invoking structures and effects that are well established in modern cosmology, even if their application to this specific case remains uncertain. If the supervoid explanation fails, more exotic alternatives must be considered, possibilities that venture into less familiar territory. Beyond the supervoid, several other explanations have been proposed that attempt to account for the cold spot using various physical mechanisms that do not require fundamentally new theories of the universe. The possibility that the cold spot is simply a statistical fluctuation, an unlikely but not impossible random variation, remains one of the explanations that some cosmologists find most compelling. Random processes produce outliers, and when we examine the entire sky looking for unusual features, we increase our chances of finding something that appears anomalous, even when nothing genuinely unusual has occurred. The cold spot might be exactly this kind of false alarm, a region that looks significant but represents nothing more than the tail of an ordinary statistical distribution. The argument for the statistical fluke explanation rests on the observation that 1 or 2% probabilities, while low, are not impossibly low. If the chance of finding a cold spot-like feature anywhere in the sky is roughly 1%, then we should not be terribly surprised to find one in our universe. We only get to observe one sky, and that sky happens to contain this feature. But 1,000 other observers in 1,000 other universes might see no such anomaly. We might simply be among the unlucky few percent. The psychological difficulty with accepting the statistical fluke explanation is that humans are not good at accepting that rare events can happen for no particular reason. We naturally search for causes and explanations, feeling uncomfortable with the idea that something notable might exist purely by chance. This cognitive bias can lead us to overinterpret random patterns, finding significance where none exists. The cold spot might exploit this tendency, capturing attention precisely because it appears meaningful, even if it is not. Cosmologists who favor the statistical interpretation often point to the look elsewhere effect, noting that the cosmic microwave background has been examined using many different statistical tests and many different definitions of what counts as anomalous. When we perform many tests, some will inevitably produce results that cross conventional significance thresholds just by chance. The cold spot might be a casualty of multiple testing, a feature that looks special only because we looked in so many places for something special. Another explanation that has been proposed involves cosmic textures, hypothetical defects in the structure of space itself that might have formed in the very early universe during a period called symmetry breaking. According to some theories, the vacuum of space could have settled into different states in different regions as the early universe cooled, and the boundaries between these regions could persist as topological defects, analogous to cracks in an ice sheet. A texture collapsing or unwinding could affect the cosmic background in distinctive ways. The texture hypothesis predicts specific patterns in the cosmic microwave background that would differ from random fluctuations, potentially explaining why the cold spot appears unusual when analyzed statistically. A collapsing texture would create a cold spot with particular geometric properties, roughly circular with a specific temperature profile from center to edge. Some analyses have found that the cold spot's properties are consistent with what a texture would produce, though this consistency does not constitute proof. No direct evidence for cosmic textures exists outside of the cold spot itself, making the texture hypothesis somewhat ad hoc, proposed specifically to explain this anomaly rather than predicted independently. The theory that predicts textures is not currently favored for other reasons, and invoking textures to explain the cold spot requires accepting a theoretical framework that most cosmologists do not find compelling. The explanation remains possible, but is not widely accepted. The possibility that multiple effects combine to produce the cold spot has also been explored, with different contributions adding together to create the observed temperature deficit. Perhaps the supervoid contributes some cooling, random fluctuation contributes additional cooling, and the combination produces the full effect. This combined explanation has the virtue of not requiring any single mechanism to explain everything. But it also has the disadvantage of involving multiple factors that may be difficult to disentangle. Instrumental artifacts were considered early in the investigation, but have been largely ruled out by the independent confirmation of the cold spot in data from multiple satellites. If the anomaly appeared only in WMAP data, we might suspect something particular to that instrument or its analysis pipeline. The confirmation by Planck, using completely different hardware and software, makes instrumental explanations essentially untenable. The cold spot is real in the sense that it appears consistently in all high-quality measurements. Some researchers have proposed that the cold spot might be related to primordial features created during or shortly after cosmic inflation, the hypothetical period of rapid expansion in the very early universe. Inflation is thought to have created the initial fluctuations that eventually became the cosmic microwave background variations, and unusual events during inflation could potentially create anomalous features. This explanation ventures into highly speculative territory, where our theoretical understanding is limited. The challenge with all conventional explanations is that none of them fully accounts for the cold spot's properties without invoking additional assumptions or accepting some degree of improbability. The supervoid does not seem large enough. The statistical fluke seems somewhat unlikely. Textures are not otherwise supported, and combinations feel contrived. Each explanation has strengths and weaknesses, supporters and critics, and none has achieved consensus acceptance. The persistence of the mystery, despite decades of investigation, reflects the genuine difficulty of the problem and the limitations of our data and theoretical understanding. Some scientific questions take a long time to answer, and the cold spot may be one of them. Patience and continued investigation are required rather than premature closure. The range of conventional explanations, none fully satisfying, has led some cosmologists to consider more dramatic possibilities, including the idea that the cold spot might represent evidence for something beyond our universe entirely. Among the most striking proposals for the origin of the cold spot is the possibility that it represents a scar left by contact between our universe and another one, a cosmic bruise from a collision between bubble universes in a larger multiverse. This idea emerges from theories of eternal inflation, which suggest that our observable universe is just one bubble among potentially infinite others, each forming separately in an eternally expanding background. If two bubbles happened to expand into each other, the collision would leave marks on the cosmic microwave background of each. The concept of eternal inflation extends the standard inflationary scenario that cosmologists use to explain the uniformity and flatness of our observable universe. Standard inflation proposes that the very early universe underwent a brief period of exponentially rapid expansion, smoothing out irregularities and setting the stage for the cosmos we observe today. Eternal inflation suggests that this inflationary process never truly ends but continues forever in some regions of space, continuously spawning new bubble universes where inflation locally stops and normal cosmic evolution begins. In the eternal inflation picture, our universe formed when a region of the inflating background transitioned to a lower energy vacuum state, creating a bubble that expanded outward at nearly the speed of light. Other bubbles would form similarly in other regions, each one potentially containing its own version of physics and its own cosmic history. The bubbles expand into the eternally inflating background and into each other, creating a vast and perhaps infinite collection of universes that together constitute the multiverse. If two bubble universes expand into the same region of the inflating background, their boundaries will eventually meet, creating a collision surface where the two distinct regions of space-time interact. The physics of this collision would depend on the properties of each bubble, but energy would be exchanged at the boundary, potentially leaving observable signatures in the cosmic microwave background of each universe. The collision would appear as a roughly circular region where conditions differed from the rest of the sky. The cold spot's approximately circular shape and its status as an anomaly in an otherwise well-behaved cosmic background have made it a candidate for such a collision signature. Theorists calculated what a bubble collision should look like and found that the predictions roughly match the cold spot's observed properties, at least in broad terms. The idea that we might be seeing evidence of another universe captured public imagination and generated significant scientific interest, even among those who remained skeptical. The multiverse hypothesis has existed in various forms for decades, arising from different theoretical considerations in physics, including the string theory landscape and quantum mechanical many-worlds interpretations. Eternal inflation provides a particular version that makes potentially testable predictions, because bubble collisions should leave specific signatures that could in principle be detected in the cosmic microwave background. The cold spot offered what appeared to be a possible detection. The appeal of the multiverse explanation lies partly in its grandeur, the idea that we might have found evidence of something beyond our observable cosmos, confirmation that reality extends far beyond everything we can see. If the cold spot truly represents a collision with another universe, it would be among the most significant discoveries in the history of science, fundamentally changing our understanding of existence. This potential significance motivates careful investigation despite the hypothesis's speculative nature. The scientific status of the multiverse hypothesis differs from more conventional cosmological claims, occupying territory at the edge of testability, where theory exceeds our ability to confirm or refute through observation. Some physicists argue that the multiverse is a legitimate scientific hypothesis because it arises naturally from well-established physics and makes predictions that could in principle be tested. Others argue that without the ability to observe other universes directly, the hypothesis falls outside the domain of science. The bubble collision explanation for the cold spot brings this debate into sharp focus, offering what might be evidence for the multiverse, while also illustrating the difficulties of testing such dramatic claims. Even if the cold spot's properties are consistent with a collision, this consistency does not prove that a collision occurred. Alternative explanations remain viable, and distinguishing between them requires either ruling out alternatives or finding additional evidence that specifically supports the collision hypothesis. The idea that our universe might have collided with another one raises profound questions about the nature of reality and our place within it. If the multiverse exists, our observable universe is not everything. It is one instance among potentially infinite others, a single bubble in an incomprehensibly vast foam of cosmic possibilities. The cold spot might be a window into this larger reality, or it might be a misleading anomaly that points nowhere. The emotional response to the multiverse hypothesis varies among scientists and the public, from excitement at the possibility of such an expanded reality to skepticism about claims that seem to exceed available evidence. Both responses are understandable given the nature of the claim. The possibility of observational evidence tips the balance toward taking the hypothesis seriously, while the difficulties of interpretation counsel caution. The theoretical development of bubble collision signatures has proceeded in parallel with observational searches, with physicists calculating in detail what such collisions should produce in the cosmic microwave background. These calculations provide specific predictions that can be tested against the actual properties of the cold spot and against searches for similar features elsewhere in the sky. The interplay between theory and observation continues to refine our understanding of what the multiverse hypothesis predicts and whether those predictions match reality. To evaluate whether the cold spot might truly represent evidence of another universe, we need to understand in more detail what a bubble collision would actually involve and what marks it would leave on the cosmos. The physics of bubble universe collisions involves the interaction between regions of space that have settled into different vacuum states with different properties and potentially different physical laws. When two such regions meet, energy is exchanged at the boundary, and this exchange leaves an imprint on the matter and radiation in each bubble. The details of this imprint depend on the relative properties of the colliding bubbles and on when, during cosmic history, the collision occurred. In the eternal inflation picture, each bubble universe forms as a region where the inflating vacuum decays to a lower energy state, ending inflation locally and beginning normal cosmic evolution. The transition creates a boundary, the bubble wall that separates the interior from the still inflating exterior. This wall expands outward at nearly the speed of light as the bubble grows, encountering whatever it encounters in the eternally inflating background, including potentially other expanding bubble walls. When two bubble walls meet, they do not simply pass through each other or annihilate. Instead, they create a collision surface where the two different vacuum states interact, exchanging energy and information across the boundary. The collision surface would have been part of the very early universe for each bubble, occurring during or shortly after the epoch when the cosmic microwave background was being created. The effects of the collision would be imprinted on the ancient light that we now observe. The predicted signature of a bubble collision in the cosmic microwave background is a roughly circular disk where temperatures differ from the surrounding sky. The disk shape arises because the collision surface, when projected onto the spherical sky that we observe, appears as a circle seen from our position at the center of our observable universe. The temperature inside the disk could be higher or lower than average, depending on the specific physics of the collision and the properties of the colliding bubble. The temperature profile across a collision disk should follow specific patterns derived from the physics of the collision, with temperature varying from the center to the edge in predictable ways. These patterns differ from what random fluctuations would produce, potentially allowing collision signatures to be distinguished from statistical noise. The search for collision signatures involves looking for these predicted patterns in the actual cosmic microwave background data, comparing observations to theoretical predictions. The cold spot's properties are broadly consistent with what a bubble collision might produce, showing a roughly circular region of lower temperature with a profile that approximately matches predictions. However, broadly consistent is not the same as confirming evidence, and alternative explanations also produce features that are broadly consistent with the observations. The challenge is to determine whether the consistency is compelling enough to take the collision hypothesis seriously, or whether it is merely coincidental. Some theorists have proposed that bubble collisions might leave additional signatures beyond temperature variations, including distinctive patterns in the polarization of the cosmic microwave background. Polarization refers to the orientation of the electromagnetic waves that make up light, and the cosmic background is polarized in patterns that reflect conditions in the early universe. A collision might produce polarization patterns different from those expected from ordinary fluctuations, providing an additional test of the hypothesis. Searches for polarization signatures associated with the cold spot have been conducted using data from the Planck satellite and other observations. The results have been inconclusive, neither confirming nor ruling out the collision hypothesis based on polarization patterns alone. The data quality in the relevant region of sky is limited, and the predicted signatures are subtle, making definitive tests difficult with current instrumentation. The collision hypothesis also predicts that there should be multiple collision signatures scattered across the sky if bubble collisions are relatively common in the multiverse. Finding just one anomaly, like the cold spot, is less compelling than finding multiple anomalies with consistent properties, because multiple detections would reduce the likelihood that statistical fluctuations explain the observations. Searches for additional collision signatures have been conducted, but have not produced convincing candidates beyond the cold spot itself. The absence of multiple clear collision signatures does not rule out the hypothesis, because the collision rate might be low enough that only one or a few would appear in our observable sky. Alternatively, collisions might produce varying signatures, depending on their specific circumstances, making them harder to identify through uniform search criteria. The lack of additional candidates weakens, but does not disprove the collision explanation for the cold spot. The theoretical framework underlying bubble collision predictions remains uncertain, with different models predicting different probabilities and properties for collisions. The eternal inflation scenario is motivated by theoretical considerations, but has not been confirmed observationally. And the details of how bubble collisions would occur depend on aspects of physics that are not yet well understood. The predictions carry theoretical uncertainty in addition to observational uncertainty. The collision hypothesis represents an extreme form of explanation for the cold spot, invoking entities, other universes, that we cannot observe directly and may never be able to confirm exist. This extremity is both its appeal and its weakness. If correct, it would revolutionize our understanding of reality. If incorrect, it demonstrates the danger of over-interpreting ambiguous data in favor of dramatic conclusions. The scientific community has generally approached the collision hypothesis with cautious interest, taking it seriously enough to investigate, but not accepting it as established. This approach reflects appropriate scientific conservatism when dealing with extraordinary claims that require extraordinary evidence. The cold spot is intriguing but not conclusive, and the collision explanation remains possible but unproven. To move toward a more definitive answer about the cold spot's origin, scientists have proposed specific tests that could distinguish between the collision hypothesis and alternative explanations. Testing the hypothesis that the cold spot represents evidence of a bubble universe collision requires identifying predictions that differ between this explanation and alternatives, then comparing these predictions to actual observations with sufficient precision to distinguish between them. The challenge is that the cold spot is a single feature with limited information content, and multiple explanations can produce features that roughly match its observed properties. Definitive tests require either very precise measurements or detection of additional features predicted by the collision scenario. One specific prediction of the collision hypothesis is that the cold spot should have a particular geometric shape, a roughly circular disk with a specific temperature profile from center to edge, determined by the physics of bubble collisions. Detailed measurements of the cold spot's geometry can be compared to these predictions, testing whether the observed shape matches what collisions should produce. Some analyses have found reasonable agreement, while others have identified discrepancies that might indicate alternative origins. The temperature profile across the cold spot provides a particularly informative test because different physical mechanisms predict different profiles. A collision should produce a specific gradient from the center to the edge, while the supervoid would produce a different gradient, and random fluctuations would produce yet another pattern. Careful measurement of how temperature varies across the cold spot region could potentially distinguish between these scenarios. The polarization of the cosmic microwave background offers another avenue for testing, because collisions might leave distinctive polarization patterns different from those produced by ordinary cosmological processes. The cosmic background is polarized in patterns that reflect the physics of its creation and subsequent evolution, and these patterns have been measured in detail by satellite missions. Searching for anomalous polarization associated with the cold spot could provide evidence for or against the collision hypothesis. Multiple groups of researchers have conducted searches for collision signatures in the polarization data using various statistical methods and theoretical predictions. The results have been mixed, with some analyses finding hints of unusual polarization in the cold spot region, while others find nothing anomalous. The disagreements partly reflect different methodological choices and different assumptions about what collision signatures should look like. Consensus has not emerged from these studies. If bubble collisions occur with any significant frequency in the eternal inflation scenario, we might expect to find more than one collision signature in our observable sky. Searches for additional cold spot-like features elsewhere in the cosmic microwave background have been conducted, looking for other circular temperature anomalies that might represent additional collisions from different directions. These searches have not produced convincing additional candidates, though this absence could reflect low collision rates rather than ruling out the hypothesis. The statistical analysis of whether the cold spot is truly anomalous at a level requiring exotic explanation remains itself a test of sorts. If careful analysis eventually shows that the cold spot falls within the expected range of random fluctuations once all factors are properly considered, the motivation for exotic explanations diminishes. Conversely, if the anomaly becomes more statistically significant with better analysis, the need for unusual explanations strengthens. Future observations with more sensitive instruments could potentially provide better data for testing the collision hypothesis. Proposed satellite missions and ground-based observatories would measure the cosmic microwave background with higher resolution and lower noise, potentially revealing features currently hidden in the data. Better measurements of polarization would be particularly valuable, as this provides information beyond what temperature measurements alone can offer. the theoretical development of collision predictions continues, with physicists refining their understanding of what signals bubble collisions would produce and how these signals might be identified in realistic data. As theory improves, the predictions become more specific and tests become more powerful. The interplay between theory and observation drives progress, even when definitive answers remain elusive. Some scientists have proposed that the cold spot might serve as a testbed for developing methods to search for collision signatures more generally, even if the cold spot itself ultimately proves to have a mundane origin. The techniques developed for analyzing this feature could be applied to future data, potentially detecting collision signatures that are currently below our detection threshold. The cold spot would have scientific value even if it proves not to be what the most exciting hypotheses suggest. The current state of testing leaves the collision hypothesis neither confirmed nor ruled out, occupying an uncertain middle ground where possibilities remain open, but proof remains lacking. This uncertainty is frustrating for those who want definitive answers, but is normal in science, where many questions take years or decades to resolve, and some may never be conclusively answered. Patience and continued investigation are required. The question of how we should respond to this uncertainty, whether to favor the exotic explanation despite lack of proof, or to favor conventional explanations despite their limitations, reflects broader questions about how science operates when evidence is ambiguous. Different scientists take different approaches, and the debate itself is part of the scientific process. Living with uncertainty about the cold spot's origin has become a normal part of cosmological practice, a known mystery that continues to generate research and discussion without resolution. More than 2 decades have passed since the cold spot was first identified in the cosmic microwave background data, and despite extensive investigation by numerous researchers using multiple approaches, no explanation has achieved consensus acceptance. The mystery persists, a stubborn anomaly that refuses to resolve itself into either a definitive detection of new physics or a satisfying conventional explanation. Scientists continue to live with this uncertainty, working on the problem intermittently, while accepting that answers may not come quickly or easily. The supervoid hypothesis continues to have supporters who believe that a sufficiently large void, perhaps combined with other effects, can explain most or all of the cold spot's temperature deficit. These researchers point to ongoing refinements in our understanding of the void's properties and in our calculations of how voids affect cosmic background radiation. As measurements improve and models become more sophisticated, the supervoid explanation may become more or less plausible, but currently it remains viable without being definitive. The statistical fluctuation explanation also maintains adherents who argue that the cold spot, while unusual, falls within the range of what we should expect to find somewhere in the cosmic background, purely by random chance. These researchers emphasize the difficulties of properly accounting for multiple comparisons and the human tendency to overinterpret apparent patterns. The cold spot might be memorable precisely because it is unusual, not because it is inexplicable. The multiverse collision hypothesis continues to attract attention, particularly from theorists interested in the possibility of observational evidence for ideas that might otherwise remain purely speculative. While proof remains elusive, the hypothesis has not been ruled out, and some researchers continue to refine predictions and develop new tests that might eventually confirm or exclude this dramatic possibility. The appeal of potentially discovering evidence for other universes keeps the hypothesis alive. The scientific process that has produced this prolonged uncertainty is working as it should, with claims being scrutinized, alternative explanations being explored, and premature conclusions being avoided. Science does not always produce quick answers, and some questions take generations to resolve, if they are resolved at all. The cold spot exemplifies this aspect of scientific practice, demonstrating that important questions can remain open for long periods, despite significant effort. The emotional experience of living with scientific uncertainty varies among researchers and the public. Some find uncertainty frustrating, wanting definitive answers to clear questions. Others find it exciting, appreciating the open possibilities and the ongoing opportunity for discovery. Still others accept uncertainty as a normal condition that neither demands immediate resolution nor prevents useful work in the meantime. All of these responses are valid. The cold spot has become part of the standard curriculum in cosmology courses, introduced to students as an example of an unresolved mystery that illustrates both the successes and limitations of our current understanding. Students learn about the cosmic microwave background's remarkable uniformity, and then learn about the anomaly that slightly violates this uniformity, raising questions about what our theories might be missing. The pedagogical value of mysteries extends beyond their eventual resolution. Research on the cold spot continues at a reduced pace compared to the initial flurry of activity following its discovery. As the low-hanging fruit has been picked, and the remaining questions require either better data or new theoretical insights. Papers continue to appear in the scientific literature, each adding incrementally to our understanding without typically providing breakthrough resolution. Progress is slow but not absent. The broader cosmological community has largely moved on to other questions, while keeping the cold spot in mind as an open problem that might eventually yield to better understanding. The resources available for any particular scientific question are limited, and researchers must prioritize where to focus their efforts. The cold spot remains interesting, but has not risen to the level of urgency that would command the field's full attention. Future observations might provide the data needed to resolve the mystery, with upcoming satellite missions and ground-based observatories potentially offering improved measurements of the cosmic microwave background and the large-scale structure of the universe. These missions are designed for various purposes, but their data will be examined for what it might reveal about the cold spot, along with other questions. The resolution might come as a byproduct of broader scientific programs. The possibility remains that the cold spot will never be definitively explained, that it will persist as an unresolved anomaly in an otherwise well-understood cosmic background. Some scientific questions turn out to be unanswerable given the limitations of available evidence, and acceptance of this possibility is part of mature scientific practice. Not everything can be known. The cold spot's persistence as a mystery reflects the authentic difficulty of understanding the cosmos based on limited observations from our single vantage point. We cannot travel to the cold spot region, cannot perform experiments on it, cannot observe it from different angles. We can only measure the light that reaches us and try to infer what produced the patterns we observe. This limitation is fundamental to cosmology. Regardless of its eventual resolution, The cold spot has already contributed to scientific understanding by motivating careful analysis of cosmic background data and by stimulating theoretical work on various explanations. Even if the mystery proves mundane, the investigations it prompted have value. Science benefits from anomalies that require explanation, even when the explanations prove elusive. The cold spot's implications extend beyond the specific question of what created it, touching on broader themes about knowledge, uncertainty, and the nature of scientific investigation. The cold spot reminds us that even our most successful scientific theories are approximations, remarkably good descriptions of nature that nonetheless leave room for surprises and anomalies. The standard cosmological model has achieved extraordinary success in explaining the universe's history and structure. Yet the cold spot represents a small but persistent discrepancy that this model does not fully account for. Such discrepancies are valuable, pointing toward the edges of our understanding, where new physics might be hiding. The history of physics contains numerous examples where small anomalies eventually led to major discoveries, observations that did not quite fit existing theories, and ultimately required new frameworks to explain. Mercury's orbit deviated slightly from Newtonian predictions, a tiny discrepancy that eventually contributed to evidence for Einstein's general relativity. Certain aspects of black body radiation seemed inexplicable, motivating the quantum revolution. The cold spot might or might not prove similarly consequential. The lesson of these historical examples is not that every anomaly points to revolutionary physics. Most do not. But that anomalies deserve careful attention rather than dismissal. The cold spot might be a statistical fluke or a supervoid effect, in which case it teaches us about statistics and voids. Or it might be evidence of new physics, in which case it teaches us something far more fundamental. Either way, taking anomalies seriously is the appropriate scientific response. The multiverse hypothesis, if it were ever confirmed, would represent a transformation in our understanding of existence, comparable to the Copernican revolution that displaced Earth from the center of the cosmos. Learning that our universe is one among many would be humbling and exhilarating, revealing that reality is vastly larger than anything we observe directly. The cold spot offers a possible glimpse of this larger reality, though the glimpse remains uncertain. The difficulty of testing the multiverse hypothesis raises philosophical questions about the boundaries of scientific inquiry and the nature of evidence. Can we meaningfully investigate the existence of other universes that we cannot observe directly? Some argue that the multiverse is inherently unscientific because untestable, while others argue that indirect evidence like collision signatures brings it within the domain of science. The debate reflects broader tensions in philosophy of science. The cold spot illustrates the challenges of cosmology more generally, a field that attempts to understand the entire universe based on observations from a single location at a single moment in cosmic history. Cosmologists cannot perform controlled experiments on the universe, cannot observe it from different vantage points, cannot wait long enough to see it evolve significantly. These limitations make cosmological knowledge different in character from knowledge gained in laboratory settings. The acceptance of uncertainty that the cold spot demands is a valuable intellectual practice, requiring scientists and science enthusiasts to hold questions open rather than forcing premature closure. The desire for definitive answers is natural, but reality does not always cooperate, and accepting this is part of intellectual maturity. Some questions take time, some may never be answered, and both outcomes are acceptable. The public fascination with the cold spot and the multiverse hypothesis reflects a broader hunger for understanding our place in existence, a desire to know whether reality extends beyond what we can observe directly. This curiosity is a valuable human trait, motivating both scientific inquiry and philosophical reflection. The cold spot taps into deep questions about the nature of everything. The value of unsolved mysteries in science extends beyond their eventual solutions, because the process of investigation generates knowledge and techniques that prove useful in other contexts. The methods developed to search for collision signatures could be applied to future data, potentially detecting phenomena we have not yet anticipated. The theoretical frameworks constructed to explain the cold spot illuminate aspects of physics that matter regardless of the cold spot's origin. The cold spot has inspired public communication about cosmology, providing a concrete example of ongoing scientific uncertainty that helps convey the nature of the scientific process. Science is often presented as a collection of established facts, but it is more accurately an ongoing conversation with nature, full of provisional conclusions and open questions. The cold spot illustrates this reality. The interdisciplinary nature of cold spot research demonstrates how modern science requires collaboration across specialties, combining theoretical physics, observational astronomy, statistical analysis, and data science. No single researcher or approach can resolve such complex questions alone. The collective enterprise of science is essential for tackling problems at the frontier of understanding. Whatever the cold spot's ultimate explanation, the decades spent investigating it have not been wasted. Knowledge has been generated, methods have been developed, students have been trained, and the scientific community has demonstrated its capacity to take on difficult questions without guaranteeing definitive answers. The cold spot has been a worthy puzzle. As we approach the end of this journey, we return to the cold spot itself, a quiet feature in the ancient light that continues to raise questions about the nature of our universe and what might lie beyond it. The cold spot remains in the cosmic microwave background, unchanged by all the analysis and debate it has generated since astronomers first noticed it more than 2 decades ago. The satellite missions that discovered and confirmed it have long since completed their observations, but the data they collected continues to be examined, and the feature they revealed persists as an unexplained anomaly in the oldest light we can observe. Whatever created the cold spot, it happened nearly 14 billion years ago, and the evidence of that creation has been traveling toward us ever since. The region of sky containing the cold spot lies in the southern constellation Eridanus, a meandering river of stars, visible from the southern hemisphere and partly visible from southern latitudes of the northern hemisphere during certain seasons. The constellation itself holds no special significance for the cosmic anomaly. It simply provides a convenient label for the direction in which this particular mystery lies. Ancient astronomers who named the constellation could not have known what their distant descendants would discover in that part of the sky. The cosmic microwave background that contains the cold spot fills all of space, present in every direction, with the same faint warmth. A relic of the universe's first light, finally freed to travel after hundreds of thousands of years of cosmic expansion. and cooling. This background radiation has been traveling for nearly all of cosmic history, crossing the vast distances of space, while the universe grew from a hot, dense beginning into the structure-filled cosmos we observe today. The cold spot is part of this ancient light. The approximately 5 degrees of sky that the cold spot spans corresponds to an enormous volume of the early universe, a region that was already vast when the cosmic background was released and has expanded further in the billions of years since then. The size of the feature contributes to its mystery because fluctuations as large as the cold spot should be rare according to our best understanding of the early universe's properties. The cold spot is larger than it should be, colder than it should be, and still unexplained. The 70 millionths of a degree by which the cold spot differs from its surroundings is far too small to perceive without sophisticated instruments. A temperature difference that would be utterly undetectable by any human sense. Yet this tiny difference represents a significant anomaly in a background that is otherwise uniform to extraordinary precision, raising questions about what physical process could have created such a distinct feature in the ancient light. The various explanations proposed over the years remain on the table, non-definitively confirmed, non-conclusively ruled out. The supervoid might be responsible, or it might not. Statistical fluctuation might explain everything, or it might not. The collision hypothesis might be correct, or it might not. The uncertainty persists, comfortable for some investigators and frustrating for others. A normal state of affairs in the slow progress of scientific understanding. If the cold spot proves to be a statistical fluctuation or a supervoid effect, it will become an interesting historical footnote, an anomaly that briefly captured imagination before receiving a mundane explanation. The excitement it generated would have been based on misinterpretation, but the investigation would still have produced valuable knowledge about the cosmic background and the methods we use to analyze it. Even wrong ideas contribute to understanding when pursued honestly. If the cold spot proves to be evidence of a bubble universe collision, it will become one of the most significant discoveries in the history of science, our first observational evidence that reality extends beyond the observable universe into a multiverse of cosmic proportions. The implications would be profound, reshaping our understanding of existence and our place within a reality far vaster than we have directly observed. This possibility remains open. The honest answer to what the cold spot is remains, "We do not know," a phrase that scientists should be comfortable using when evidence does not support confident conclusions. Not knowing is not failure. It is the accurate representation of our state of understanding on a question where the data does not yet provide a definitive answer. The cold spot may always remain unexplained, or explanation may come tomorrow. Either is possible. The universe presents itself to us with both answers and questions, revealing its nature through the light that reaches us, while keeping some aspects hidden or ambiguous. The cosmic microwave background is one of the clearest windows we have into cosmic history, confirming our theories with remarkable precision while also presenting the cold spot as an unresolved puzzle. The combination of confirmation and mystery is typical of how nature yields to investigation. The night sky above us contains the cosmic background invisibly, present in every direction though undetectable by human senses, filling the dark between visible stars with the faint warmth of ancient light. Somewhere in that background, in the direction of Eridanus, lies the cold spot, cooler than its surroundings for reasons we have not determined, a quiet mystery waiting in the cosmic dark. The contemplation of cosmic mysteries can be peaceful rather than troubling, an opportunity for wonder rather than frustration, a reminder that the universe is larger than our knowledge and richer than our understanding. The cold spot invites this contemplation, presenting a question without demanding an answer, suggesting possibilities without confirming any of them, existing simply because it exists, regardless of whether we ever understand why. The ancient light continues its journey, having traveled for nearly 14 billion years to reach us, carrying information about the early universe and its fluctuations, including whatever created the cold spot so long ago. The light will continue traveling indefinitely into the cosmic future, spreading through expanding space, growing fainter with time, carrying its mysteries onward, even if we never solve them. The universe keeps its own time. The investigation of the cold spot will continue, slowly, as researchers examine new data, develop new theories, and refine their understanding of what the observations might mean. Perhaps resolution will come, or perhaps the mystery will persist indefinitely, joining the collection of open questions that science accumulates alongside its answers. Either outcome is acceptable. The cold spot waits in the southern sky, in the ancient light, in the cosmic microwave background that fills all of space. It may be a statistical fluctuation, an effect of cosmic structure, evidence of another universe, or something we have not yet imagined. The question remains open, the mystery remains gentle, and the night remains full of wonders, waiting to be noticed, understood, or simply appreciated for what they are.